Hey y'all, welcome back. Tonight's homework is all about learning how to convert equations using a technique called eliminating the parameter. So number one, we're trying to express y as a function of x. And basically what that means is we want to rewrite the equation for y so that instead of having our variable t here, we just have x. So the first thing we need to do is rewrite this x equation so that t is isolated. So I'm going to start by just rewriting the equation here and solve for t. So in that case I would subtract 1 from both sides and then divide both sides by 2. So I'll get t equals x minus 1 all over 2. And now that I have t in terms of x, I can use this expression here. Oops. Okay. I can use this expression here to substitute it back into t for the y equation, and then just simplify after that. And so what that's going to do is give our equation for y in terms of x rather than t. So we're converting this from a set of parametric equations to a single rectangular equation. So what we end up with here is y equals x minus 1 over 2, and I'm writing that instead of t, minus 1. And you could definitely simplify this a little bit. For instance, we can separate this expression up here and divide each term by 2. So that would be y equals x over 2, or 1/2 x minus 1/2. A better way of writing this x over 2 is probably going to be 1/2 x. And then you have this minus 1 still kind of hanging out here, right? So basically just separating out this fraction by dividing each term by 2. So you get 1/2 x minus 1/2, and then you got the minus 1. From there you can combine these. Negative 1/2 minus 1 would be negative 3/2, or negative 1.5. Either one of these answers would be acceptable. Would just be sort of the better of the two answers. It's the more simplified version of it, and you can see exactly, like, it's already in slope-intercept form, and it'd be a lot easier to graph. But this one works just as well. So if you want to stop here, you have sort of satisfied the requirements of the problem. So number 2, we're going to solve all 4 of these exactly the same way, where we're going to start by solving for t in terms of x. So I'm going to take this first equation, and I'm just going to rewrite it here. X equals t plus 3, and I would subtract 3 on both sides to isolate t on this one. So I'd get t equals x minus 3. And so this is the expression that I can use to substitute in for t back into the y equation. So I'm just going to put it right here. And so I get y equals that expression, x minus 3 squared. Depending on kind of what you're going for, I mean, this answer is good and fine. Nothing wrong with this. If you did square this out, you would get y equals x squared minus 6x plus 9. But that's not really necessary, like, unless the problem specifically needs you to have it in standard form. This doesn't ask for that. Kind of the same thing that I was referring to over here, where it doesn't really ask you for this equation in slope-intercept form, but if you needed it to for graphing purposes or something, it might be useful. But even over here, it's probably easier to graph it not in standard form anyway. So this is probably going to be the better of the two answers, but either one's fine. And what we've done, and like I said, the goal here is to express y as a function of x. So we've written the equation y equals in terms of x. One thing that this whole process is really good for is if I give you a set of parametric equations and you're not really sure what looks like, you can convert it to this rectangular form where you're more familiar with some of these shapes. Like you can see that this is going to be a line, you can see this is going to be a parabola, where just looking at the parametric equations themselves, sometimes it's not as obvious because you're not as familiar with them. So let's take a look at 3 and 4. We're going to use the same sort of strategy, but it doesn't look like this is going to be quite as straightforward as far as what equation it turns out to be, but let's just let's see how it turns out. So we're going to rearrange this first equation just like we did on 1 and 2. In fact, let me just stay consistent with the color here. So we started with x equals 4 minus t, and we would want to do actually 2 steps here. The first thing we would do is subtract 4 on either side, and then and to get rid of this minus or this negative, this opposite symbol, we'd want to divide both sides by -1 or multiply both sides by -1. It's essentially the same thing, but either way what you'll effectively do is just swap the signs for each term. So dividing both sides by -1 would make this negative, this positive, and this positive, which is kind of what you're going for here. Okay, now t is isolated. So just going to rearrange it here and say t equals, and we get -x plus 4. So this is going to be the expression that we'll use to substitute into the y equation for t. And so we get y equals the square root of, and not t anymore because now we know what t equals in terms of x, -x plus 4. And so this is our equation. Not really anywhere you particularly need to go with this after this. There's not going to be like another standard form that you can get it into. This one's pretty good. So that would be your answer here. Number 4, we are going to start it out just like the other ones. Solve for t in terms of x. So I'm going to start just the same way I did with the other ones. Just with the equation itself, and then from here you can see you would need to multiply both sides by 2 to isolate t, and we would get t equals 2x. This is the expression, this 2x here, that I'm going to substitute into t for the y equation right here. And so what we end up with is y equals 1 over, and instead of t we've got 2x plus 1. And that equation looks good to go too. So there you go, there's 1 through 4. All of these you can kind of work in the same way. You know, I guess I kind of feel like I should have boxed this one to stay consistent with everything else that I did. Either one's fine, just like what we were saying earlier in the video. But yeah, so the overall strategy here is to solve the x equation for t, plug that into the y equation, just simplify if need be. So that's it. Let's take a look at the next set of problems, which it says find a set of parametric equations for the rectangular equations that are given. So we're given 3 different rectangular equations using the parameter t equals 2 minus x. Now, when you're trying to convert from rectangular equations to parametric equations, you need to be given a parameter. Otherwise, you know, you just have to make one up, and then it's kind of sort of pointless. So you need to have some information about the relationship between your third variable and one of the 2 other variables, not necessarily both of them. And really what we're trying to do here is figure out the other one. So we've got the equations are given in rectangular form, and what we're going to do here is we are going to solve this equation t for x, kind of like the reverse of what we did up here. And once we have that solved, we're going to plug that in to x to get the other equation. So let's start by solving this one for x. And what that's going to do for us is it's going to give us one of the 2 equations for each one of these. So all of these will have the same x equation. So we'll start by subtracting 2 from either side, which will give me t minus 2. equals negative x. And just like what happened up here when I had that negative, where was that? Which one did I have to flip it all? Oh yeah, right here, where I had to divide both sides by -1. Doing the same sort of thing here, which would reverse all the signs. So this would become negative, this would become positive. So this is what our x is going to equal. I'm going to just rearrange this as x equals. Notice that this equation for x is already in terms of t. So when we're trying to come up with a set of parametric equations, this one's given for all of these, which is kind of nice. So you have this group of problems that are all using the same parameter, so they all have the same x equation. So I'm going to go ahead and copy and paste this over and over again because we have half of our answer here. I guess I'll put it down here to be a part of the answer box that we're going to create here. Alright, so there's the x equation. We're going to come up with a y equation as well, but this way we're kind of ready to go with our answer. Now to actually get the y equation, we use the equation that's given, and we're going to substitute what we know x equal to be in terms of t already, and then simplify. So for this one, we have y equals 3 times negative t plus 2. Right? That's what we're writing instead of x, and then minus 2. So from here we're just going to simplify. We need to distribute the 3. So we get negative 3t plus 6, and then we have that minus 2 kind of hanging out, and then 6 minus 2 is 4. So this is going to be our y equation. I guess I can write that as a separate step here. And there you go. So this is the set of parametric equations that would result in the same graph as this one, but with this parameter defined. So it gives you a sense of the speed of the object that is moving through that path. Number 6, we're going to do the same thing. We're going to substitute all of this in for x when we rewrite this equation. So we've got y equals, and then in parentheses, I'm going to raise this to the second power, and then have plus 1. Now, this is probably fine. You don't really need to go further than this, but if for some reason it asked you to write it in standard form, you would want to square this out. And then simplify. But honestly, like, there's not really a reason to do that. So I'm just going to leave that as my equation for y. And then looks like my box is not big enough to accommodate the length of the y equation. Okay, so number 7, we've got y equals 1 over 2x. So we're going to substitute negative t plus 2 into x into this equation. And we'll simplify if necessary. So we've got y equals 1 over 2 times x, but instead of x we're writing negative t plus 2. I'm going to go ahead and distribute that, and I think that's about as far as I'm going to take it though. So we've got 2 times negative t is negative 2t, and then negative 2 times 2 is going to be 4, so plus 4. And that looks pretty good. So I'm going to throw that in my little answer box, and there you go. There's 5, 6, and 7 just right in a row like that. So far now we've gone over how to convert from a set of parametric equations to a rectangular one, and we've also gone over how to go from a rectangular equation to parametric equations. Let's go on to page 2 here. It says find the values for t for which the curve passes through the point P. And so what this is giving you is an xy coordinate on the plane, and we're trying to figure out when does the object actually hit that point. So what we need to do, and it may not hit that at any given point, but what we need to do is we're going to use this x and this y, plug them into these equations, and check to make sure that we're getting the same t value. So one little strategy I like to use is to solve the simpler equation, or the one that looks like it's going to have fewer solutions. And instead of having to solve the other one, just check the t values that you get. Now, if both of your equations have infinitely many solutions, you might be out of luck with this strategy, but it should get you through most, if not all, of these problems. So as we go through these, I just want to point out that I'm trying to do the same steps on each one. So number 8, we are going to try to figure out, okay, well, x has to be 16 and y has to be -8 at some time, or it doesn't have to be, but if it does, we can find it by substituting these in for x and y. So let's start with the equation that looks a little simpler, and both of these are linear, so there's not really a high degree of difference in terms of the complexity of these, so you can't really go wrong picking either one, but this one has fewer terms, so I'm going to go with this one. And I'm going to say that, okay, well, y is equal to -2t, and I'm trying to find the t when the y is -8. Okay, so from here, we can just solve this equation by dividing both sides by -2, and we get 4 equals t. So this is a potential solution here. The whole thing is that just solving one of these equations does not guarantee that the other one is going to have that, that this is going to satisfy the other equation. So you need to check this t value in the other equation and make sure that that x value is what it's supposed to be. So I'm just going to make a little note here, checking the other equation. Check your possible t values in the other equation. And then, here we can verify that whether or not this is a solution, or maybe it's not. Maybe there's no solution, but let's find out. So the other equation is the x equation. So we've got x equals 3t plus 4. And we're going to check this value 4. And we want the x value to be 16. Okay, so let's see if that is true. So 3 times 4 is 12, right? 12 plus 4 is 16. That is what we want it to be. That is that checks out, so to speak, right? That is the same as the x that we are looking for. So that means our solution here is going to be t equals 4. For number 9, looks like the simpler equation is going to be the y equation, so I'm going to solve that first. This up here, this x equation, has 2 potential t values if I solve for when x is 0. So this one will have 2 potential t values and this one will only have 1. So that means that one of these t values is not, the object is not going to be at 0,4. So let's figure out which one it is, but to narrow it down, we'll just check it in the y. Okay, so we'll solve the y equation. So the y equation is y equals t plus 1, and we're going to substitute y for 4. So we're going to say, okay, 4 equals t plus 1, subtract 1 on either side, and we get t equals 3. And so this is going to be a potential solution that we can check in the other equation. So the other equation is x equals 3 squared minus 9, and we're looking for it to become 0, and let's see if it does. So 3 squared is 9, 9 minus 9 is 0. So that checks out. That's going to be our solution, the t value anyway, because we want this to be 0. So our solution, the time at which the object is at 0, 4, is at time equals 3. Uh, 10 looks like this absolute value equation. Will that have 2? I think that's going to have 2 solutions when x is 8, yeah. And then this one is only going to have 1. Okay, so you can kind of tell based on like the shape of the graph. right? And you're kind of thinking about the horizontal line test here. We don't really need to get into all that. But basically, you just need to look at the one and decide which one do you think is going to be easier to solve and have fewer solutions. So let's, and if you're not sure, you can just pick one. And, if you end up with multiple possible t values, you'll just have to check them all. For instance, like back on number 9, if I would have just solved the x equation, I would have had 2 t values to check, plug them both into the y equation, and find out that only one of them would work. So you can't really go wrong on which equation you choose to solve first. You just might make it more efficient if you are able to figure out which one is going to have fewer solutions. So we have 3 equals the square root of t plus 1, and we're solving for t here, so I'm going to start by squaring both sides, and then I'm going to subtract 1 from either side, so I get t equals 8. So this is a potential solution which I'm going to check using the other equation. I guess I should say check possible t values using the other equation. So the other equation is x equals the absolute value of t, which we're going to plug in 8. And what we're looking for is it to be 8. And so absolute value of 8 is 8. So we're good to go. And this number checks out with the x coordinate of the point. So we're good. And our solution will be t equals 8. For number 11, we're going to follow the same kind of process here. We've got a sinusoidal function, which, as we all know and love, has infinitely many solutions when you are trying to solve for a constant. And then this is a quadratic, so that's going to have 2 solutions. So we're probably better off trying to solve this second one. So let's solve this one first. And then we'll use those solutions that we'll get from this equation and check them in here and make sure, find which one is giving us the correct point. Or maybe both of them will. We'll see. So y equals 4t squared minus 5t. And we want the y coordinate to be 0. We're trying to find at what time is the point, or whatever the object is, at 0, 6. So that's going to be 6. So this is going to be a nice little quadratic here. So I'm going to subtract 6 from both sides. And we can either use quadratic formula here, or we can try to factor this. And this one appears to be factorable. So yeah, it's going to be 4t plus 3 times t minus 2. And then once you've got it factored, you can set each factor equal to 0 and solve them individually. And we're using, or taking advantage of, the 0 product property here. So we get 4t plus 3 equals 0. Or we get t minus 2 equals 0. So for this first one, we're going to subtract 3 and then divide by 4. And that's going to give us t equals negative 3/4. And we have or. We get, if we add 2 to both sides here, we get t equals 2. So these are 2 potential solutions that we need to test into the other one. So for problems 8, 9, and 10, we just had 1 solution to test. So it was like, okay, well, it either is going to be an answer or there's going to be no solution. Here, I'm not so convinced that they're both going to be solutions. Maybe one will be, maybe both will be, maybe none will be. So either way, we have to substitute these into our x equation for t and see if any of these are going to give us an x value of 0. That's what we're looking for. So we have x equals sine of pi over 2t and in this case we're going to say t is negative 3/4, and in this other case we're going to say that t is just 2. So let's simplify this a little bit, okay? When I multiply pi over 2 by negative 3/4, what I'm going to end up with is negative 3 pi over, let's see, 2 times 4 would be 8. So we're going to get something that is not likely going to be a solution here. We can put that in the calculator. This is not going to be a common angle on our unit circle. We could figure it out using, like the half angle formula, or I guess that would probably be the one to go with, and find an exact answer here. But what we want is for the x value to be 0, and that's only going to happen. Let me bring up the unit circle real quick. The only time that the sine value or the y value is going to be 0 is going to be at like increments of like 0 or pi or 2 pi or things like that. So this negative 3 pi over 8, which would be like, what would that be? Halfway, so 3 pi over 4. Gosh, I don't know. It'd be kind of near 3 pi over 2, but close, like in quadrant 4. So I'm thinking like in between 5 pi over 3 and 3 pi over 2. But anyway, the y value is definitely not going to be 0 here. So this is not going to be a solution. We'll put it in the calculator to figure out exactly what it is, but what we need it to be is 0. So this one's not going to work out. This one, on the other hand, we have sine of, well, let me just copy all this instead of rewriting it. We've got 2 times pi over 2, so that'd be like 2 pi over 2, which would be sine of pi. And as we can see on the unit circle, sine of pi is 0. So this one is going to check out. Right, this 0 that we're looking at is right here. Let's just, for kind of fun here, let's pull up the calculator and figure out what that sine of negative 3 pi over 8 is. If I had to guess, I would say, well, it's in between negative root 3 over 2 and negative 1, so I'm going to go with like negative 0.8, something like that. But let's find out. I'm in radians, so that's good. We've got sine of negative 3 pi over 8. So yeah, if I'm gonna ballpark, I'm gonna say like negative 0.8. Ooh, it's even closer to 3 pi over 2 than I thought. So yeah, negative 0.9. All right, so that's approximately what it is. We don't, it's gonna be approximately negative point, we'll say 924, just to kind of get a little more accurate there. You don't really need, all you really need to know is that it's not 0, so it's not going to be a solution. So the only solution that we end up with here is this t equals 2. Yeah, you can't see that negative 9. Hold up. Try to squeeze that on there. Okay, so, geez, let's write our answer here. All right, so our answer is just going to be t equals 2. And I'm going to need to squeeze this in here so I can have some room for number 12. But yeah, that would be our final answer here. Okay, now that I've made some room for 12 here. Oh, I forgot to pause it. Oh, well, they all got just left in the video. Okay, number 12, we've got a logarithmic function, and we've got a rational function. These are two functions that you looked at in Algebra 2, and we will look at a little closer in a future unit. But either way here, we're going to end up with just one solution, so it doesn't really matter which one we pick to solve first. Just kind of go with your gut, which one seems simpler to you. If I had to guess, I would say, gosh, I'd probably say you probably don't remember how to do it. If there was one equation that you might be a little more shaky on, it'd be the logarithmic one. So to be on the safe side, I'm gonna guess you probably solve for this one first. So we want the y to be 1/2, 0.5, same thing. So 1 over 1 plus t. So we're going to solve this for t. I guess what we can do here is a little cross multiplication here. Use a cross products property and multiply 1 by 1 plus t, and 1 times 2 would be 2. And then we would solve that by subtracting 1 from either side. So we would get t equals 1. And so what we're going to do is test that in the other equation. Now, if you don't remember how to evaluate a logarithm, you might need to use a calculator for right now, but we are going to have a whole unit kind of reviewing exponential functions and logarithmic functions, so don't feel too bad if you can't remember that. We are definitely going to hit that in a future unit. So I will go ahead and plug this back into t for the x equation, and what we're looking for is the x to be 0, and the natural log of 1 is 0. So the reason why, the short answer for why the natural log of 1 is 0 is because e to the 0th power is 1. Again, we'll talk about that more in detail in a future unit. But even if you just went ahead and put that in the calculator, you can see that this is the correct x value that we want. So we're good. We're done there. We can say that our solution here is going to be t equals 1. I'll just put a little. Number 4, 14, 15, 16, looks like we're all dealing, well, let's see what the directions say here. Find the values of t for which the parametric equations satisfy the given condition. Okay, so we've got a set of parametric equations for each one of these, and we're just trying to satisfy one particular condition. So the first one says, when do the parametric equations have an x-coordinate of 2? So we just want to set the equation here equal to 2, the x equation. So we got 2 equals t squared minus t, and we just need to solve this. So this looks like it will hopefully end up being a factoring problem. It may turn out to be to where we need to use quadratic formula to solve it if it doesn't factor, but I think it is going to factor. So we start by subtracting 2 from both sides, and then, yeah, this one is going to be factorable. So we get 0 equals t minus 2 times t plus 1. And you can check that factoring by foiling it out, if you try to factor it and just can't figure it out. Go back and look at some of my old factoring videos from Algebra 1 if you want me to go into a lot more detail on how this factoring works. But once we have it set equal to 0, we are going to set each factor equal to 0, and we'll get t equals 2 because we'll have t minus 2 equals 0, and so when we add 2 to both sides from there, we will get t equals 2. And from this factor, we will get t plus 1 equals 0. So when we subtract 1 from both sides, we get t equals negative 1. And so these will be our two solutions. These will be the 2 times that the x-coordinate, or the object, will have an x-coordinate at 2. I guess grammatically here we would want to say, like the way we would answer the question is that we would say at time 2 and -1 we have the object's x coordinate is at 2. So I guess we do want to say and here, even though like logically you would say or if you're just trying to solve the. Oh, well, anyway, I'm kind of getting in the weeds here. Just basically trying to say that these are the two times where x is going to be 2. Number 15, it says, when are the parametric equations in quadrant 4? So they're going to be in quadrant 4, which is this quadrant right here. Here's 1, 2, 3, 4. When the x is positive and the y is negative, okay? The y is positive up here, and the y is negative, or the x is negative over to the left. So in this quadrant, we're going to say that x is positive, so the x has got to be greater than 0, and the y is negative, so the y coordinate has to be less than 0. So what we need to do is we're going to solve a compound inequality where both of these are true. So we've got t minus 4, which is x, that has to be greater than 0, and we have to also satisfy the condition that y is less than 0. So t squared minus 8t plus 12 has got to be less than 0. So solving compound inequalities is something you probably did in Algebra 2. Basically, we need to find solutions to both of these, not just one of them. So the solution here would be t is greater than 4. We just add 4 to both sides. Here we would need to factor to actually, well, this is something that I guess we haven't quite gone over yet. But let me give you a little tip for right now how you can solve it, since we haven't really gone over solving polynomial inequalities. But you may have done a little bit of this in Algebra 2, but don't get too hung up if I kind of lose you here on this one. So this would factor to give me x. How would this factor? Let me think about that for a second. Minus 6 and x minus 2, or t minus 6 and t minus 2. And so what that means is, like, if you're trying to visualize this, we've got solutions here at negative 6 and 2, or I'm sorry, positive 6 and positive 2. And we want to know, when is this function going to be less than 0? In other words, when is it going to be negative? And so for all these values that are less than 0, or less than 2, like 0, like for instance, if I just plug in 0 here, 0 is going to be a negative, 0 minus 2 is going to be a negative times a negative is a positive. So this is going to be positive here. That's not going to be where it's negative. In between 2 and 6, you could pick a number 4 and say, okay, that's going to be a negative times a positive, negative times a positive is negative. And then finally, if I pick like a really big number like 100, this would be a positive times a positive is positive. So when is the function less than 0? Well, it's going to be less than 0 between 2 and 6 here. So so here we would say that t would be in between 2 and 6. Again, this is a concept that we'll hit again in a future unit. I'm not going to try to throw any of these kind of problems at you like on a quiz or anything. It'll be more based on more linear ones if I'm going to throw an inequality at you for now. So we still need to figure out where the overlap here is, because this is saying the solutions are between when t is in between 2 and 6, and this is saying when t is greater than 4. So when we're talking about a compound inequality here, we do have to satisfy both of these. And so t being, like, if this is a number line, here, let's draw a number line down here. So here's 0. That's not really relevant here, but I like to throw that on here. Here's 2. Here is 4, and here's 6. This first inequality says t is greater than 4. So all the numbers bigger than 4, or on this side of the number line of 4, would satisfy this inequality. This other inequality says that t's got to be in between 2 and 6. So that means I'm in between these two values, right, would satisfy this inequality. So the only values that would satisfy both of these, where not only is t greater than 4, but t is in between 2 and 6, is going to be in this overlapped region where we've got solutions that satisfy both of these. And so our final answer here would be that t is in between 4 and 6. So as long as t is in between 4 and 6, we can guarantee that the coordinates are going to be in quadrant 4. So that's kind of a tough one. There's a lot going on with that problem, but I think this will be a good little preview for what's coming up. Number 16, we want to know, when does it pass through the origin? So this, you just kind of have to know, okay, well, what does origin mean? That means you're at the point 0, 0. So we want to find, when do these both, what time are these both 0? We've got two sinusoidal equations. Like first of all, when is cosine 0? When is cosine of an angle measure 0? And when is 1 plus sine of that angle measure 0? Now if we solve this second equation for sine t by subtracting 1 on both sides, we get sine t equals -1. And so basically we're asking what time, or you could think about it as like an angle, what angle measure has a cosine equals 0, the sine equals -1. So the x is 0, y is -1. Let's take a look at that unit circle. When does that happen? Oop, moved the wrong thing there. So 0, -1 is right here at 3 pi over 2. So the t value would be at 3 pi over 2. Now, this doesn't have any restriction here, so it could be at 3 pi over 2, but it could also be any angle coterminal to 3 pi over 2. So like we could add or subtract 2 pi from this and get more solutions. So just kind of going back to our solving trig equations unit, we want to put this solution inside brackets, and we're going to say plus 2 pi in. And so that'll give us all the solution. On this last page, we're just finding points of collision if they exist. So what we're going to do for 5 and 6, and then we'll talk about 7 later, is we're going to first find potential points of collision, and then we will, so those potential points of collision would be the intersections, and then we'll test to see if there's an actual collision. So let's go ahead and do number 5. We'll start by picking either x or y. In this case, I think it might be easier to start with the x's and set those two equations equal to each other to give us a potential time when the collision could occur. So I'll start with the x's and say 2t plus 1 equals 9 minus 2t. And so we're going to solve this by first adding 2t to both sides, and I'll get 4t plus 1 equals 9. And then we'll subtract 1 from both sides and get 4t equals 8. And finally divide both sides by 4 to get t equals 2. So this is a potential time for when the collision exists. So basically what we're going to do is we're going to take this t equals 2, we're going to plug it into all these equations and see if they were at the same place at the same time. So at time equals 2, we're saying, hey, if there's a collision, it's happening at this time. So let's double check. We know that the x's are the same there. We do need to figure out what the x is going to be. But so let's just test. We're going to basically plug this into all 4 of these equations and see if particle A has the same coordinates as particle B. So for particle A, we've got x equals 2 times 2 was the time when this could potentially happen, plus 1. And that would be 4 plus 1 is 5. Okay. And the y coordinate would be t squared, so that'd be 2 squared. So 2 squared is 4. Okay, so we know at time 2, so, and I'll just maybe make a little note here, at time 2,
particle A is at 5, 4. And so if there's a collision, we would expect particle B to have the same coordinates. It's possible that there's not. If not, we'll just say there's no collision. So for here, we're going to use the same time value, t value, because we're wanting to see, are they both at 5, 4 when t is 2. So x is going to be 9 minus 2 times 2 in this case. So 2 times 2 is 4, and 9 minus 4 is 5. So they have the same x coordinate, which we kind of already knew that they were going to have the same x, because that's what we set equal to each other to begin with. But now we know what that x is. And we got some verification here. So for the y coordinate, we've got 2 times t, which would be 2, and that is also 4. So notice how the x's and the y's are the same, right? We've got 5, 4, 5, 4. So we can say that at time equals 2, not just particle A and B are both at or we'll say the two particles collide at 5, 4. For number 6, we'll approach it the same way. You want to look at these equations and see which one's going to be easier to set equal to and solve. Going back to number 5 just momentarily, I could have set the y equations equal to each other, but then I'm having to deal with a quadratic versus just a linear. And usually that's going to be a little bit easier to solve. So with number 6, it doesn't really look like there's a huge difference. I'm just going to go with the x's again. You can solve for the y's, that's fine, but I'm going to go with the x's on this one. So we've got 1.5t equals 3t minus 10. Either way, you would end up with a linear equation, so it's not like one's going to necessarily be easier than the other. I'm going to subtract 3t from both sides here. So that would be negative 1.5t equals negative 10, and then divide both sides by negative 1.5. Oh gosh, I'm gonna have to pull up the calculator on that one. Let's see what we get here. Not entirely sure. Haven't used the calculator a ton, but I'm gonna go ahead and do that here. So we get negative 10 divided by negative 1.5. I think we're gonna have to write that as a fraction. Yep. So let's see what that's gonna be. 20 thirds. All right. So t is 20 thirds. About 6.66. Or 6.67. And so this is our potential collision time. Okay, so we're going to figure out where particle A is at that time and where particle B is. So particle A is x coordinate will be 1.5 times 20 thirds. And I kind of am getting the feeling I'm going to need to keep that calculator up. So let's see. Let's pull that calculator back up. So we have 20 thirds times 1.5. Come on. There we go. 20 thirds times 1.5 is 10. Okay, so that's kind of nice. So the x coordinate is going to be 10, and the y coordinate will be at 0.5 times 20 thirds. And let's see what that equals. Let's go back to the calculator here. We've got 20 thirds times 0.5, or 1/2. And that's going to be 10 thirds. Okay. So as long as particle B is at that same place, we have a collision. If not, then we don't have a collision. And then we could just say there's no collision. These two particles won't run into each other. So we've got x equals 3 times the 20 thirds. Now the x should almost for sure, if the x is not the same, then that means we did something wrong in the solving over here. So whichever one you sort of set up first, you are definitely expecting it to have the same coordinates. Since we set the x equations equal to each other, really expecting this to be 10. So we got 3 times 20 thirds minus 10. Let's just plug that in. We really don't need a calculator for this, right? The 3's cancel out. 20 minus 10 is 10. But just in case you don't believe me, oh wait, I don't even have it up. There we go. 3 times 20 thirds minus 10 is going to be 10. Yep. So the x-coordinate's 10. Again, if our algebra was good at the beginning, we're sort of guaranteed that these are going to be the same. It's the y-coordinate that needs to be the same in order for there to be a collision. If it's not, then there's no collision. So negative 1.5 times 20 thirds plus 15. Not even going to bother trying to do that one in my head. Well, it might be doable if I just like stopped and thought about it for a minute, but this is going to be a little faster here. So we get, oops, well, it's not going to be faster if I mistype everything. Let's just start over there. Okay, so negative 1.5 times, I'll just grab it up here. What was it, 20 thirds plus 15. All right, so we get 5. Okay, so that means there's no collision, okay, because this time was the only sort of potential time there could be a collision. So if the collision's not happening here, it's not happening ever. Okay, so if we really want to answer this completely, we would say since particle A, or I guess we'll just say particle A and B do not collide because or we'll just say because they are not in the same location when t is equal to 20 thirds. So the key takeaway here is that there basically is no collision. All right, so there's number 6. A lot of review, especially with these trigonometric equations. We even had some quadratics, we got some cubics, a lot of Algebra 2 review going on in this unit, and even a little bit of preview for what's coming up. So this is definitely not the easiest homework we've had in a while, but hopefully you got a lot out of this, and as always, reach out if you have any questions, and I'll be sure to help you out. Y'all have a great day, and I'll see you next time.